Hello friends, today at the request of some of my subscribers I have prepared an explanation about the Carnot cycle. More precisely, we will talk about the Carnot cycle efficiency formula. Let's try to figure it out. To do this, I will first have to draw a Carnot cycle in the coordinates of pressure and volume. As you know, the Carnot cycle consists of two isotherms and two adiabats. I draw slowly, but I don't like to rush. I think students don't understand when a teacher explains quickly. What do you think about it? I have identified 4 points of transience in order to most conveniently describe the process taking place. So we have isotherms and there are also adiabats. The cycle must always be closed. I will need to apply the first principles of thermodynamics for each process. I hope you remember what the first beginning of thermodynamics is. The first principle of thermodynamics is the law of conservation of energy of our thermal processes. In the process 1 point, 2 points, an amount of heat is supplied to the gas at a constant temperature. In the process 2.3 points, which in this case is adiabatic, the amount of heat from environment does not arrive. The system performs work only by reducing its internal energy. When moving from point 3 to point 4, the system releases an amount of heat into the environment, which is called a refrigerator. I would like to consider in detail some process, for example isothermal. To do this, I am writing the first beginning of thermodynamics. Within the framework of the first law of thermodynamics, the amount of heat is spent on changing internal energy and on performing work. If the temperature is constant, then the temperature change is zero, and therefore the change in the internal energy will also be zero. This means that all the supplied amount of heat is spent only on doing the work. Infinitesimal work will be depicted on their pressure and volume diagrams as follows. Now I have to remember the Mendeleev-Clapeyron equation and express the pressure, which is what I'm doing now. Now this pressure needs to be substituted into the formula of infinitesimal work. Replace the infinitesimal work with a differential and we get an equation that needs to be integrated. In the coordinates of pressures and volume, this is the area of the shaded figure. So I found a work for an isothermal process. Now I will find a work for the adiabatic process. Similarly as in the case of an isothermal process, I will use the first principle thermodynamics. I will draw the adiabat again. It looks like an isotherm, isn't it right? Applying the first principle of thermodynamics, I take into account the fact that in an adiabatic process the system is isolated from the surrounding heat and the amount of heat supplied in this case is zero. The system performs its work by reducing its internal energy. I'm writing the Poisson equation. The kappa symbol is an adiabatic exponent. Some textbooks use a different gamma symbol, but I am used to using the kappa symbol. I hope you remember Meyer's formula, which relates the heat capacity on constant pressure and volume. Now it remains for me to write a paper using the first principle of thermodynamics for an adiabatic process. This formula can also be written using molar heat capacity at constant volume. Let's go back to our drawing and look at it. It is obviously that in section 1.2 points the system received the amount of heat, and in section 3.4 point the system gives the amount of heat. It remains for me to calculate the total work. To do this, I separately show the work and the amount of heat for each process. While I'm writing, I would like to invite you to subscribe to my YouTube channel and Telegram. I also invite you to follow our Telegram community, and of course do not forget about my t-shirt and visit the branded clothing store for people of science. I will leave the links in the description of this video. So let's find our work. Note that on the section 2.3 point and on section 4.1 point the system performed the sum modular work, but opposite in sign. Therefore the sum of this work is 0. I will write down the Poisson equation again to consider section 2.3 points and 4.1 points. If, for example, we also apply the Mendeleev-Clapeyron equation to the 2.3-point process, then we can get a slightly modified Poisson formula. I have once again written the Mendeleev-Clapeyron equation to remind you that it is very often used in the appropriate place. We shall do the sum for process 4.1 points. Thus I proved that the ratio of volumes V1 to V2 is equal V4 to V3. Now to find the efficiency you have to divide the work by the amount of heat supplied. As already proved earlier, the flux is equal to the difference in the amount of heat Q1 minus Q2. Now it remains to put the appropriate amounts of heat in the efficiency formula and introduce some values. As you can see, the mass, molar mass, universal gas constant and logarithm are reduced and we get the temperature ratio. Do not forget that the temperature is measured in kelvins, and it turned out that at absolute zero the efficiency of the heat engine should be equal to 100%, but absolute zero is not reached. That's all for now. I have finished, and finally invite you to also follow our community in Telegram, write comment, subscribe to my channel. All by sincerely Yuri Kovalenok.